Alright, in this video we're going to start section 2.2, and that is finding limits graphically and numerically. And we have 3 bullet points. The first one is estimate a limit using a numerical or a graphical approach. The second one is learn different ways that a limit can fail to exist. There's 3 of them. And the last one says study and use the formal definition of a limit. We're not going to cover that in this class. I took an AP Academy a couple years ago, and I was advised by the guy running that not to teach that formal definition in Calc 1. You know, that's something you will see later on if you continue calculus in college. And the time spent on that formal definition of a limit, which is pretty confusing, that time could be better spent elsewhere getting you ready for that AP test. So here's an introduction to limits. Suppose you're asked to sketch the graph of the function f given by this, x to the third minus 1 over x minus 1. At what value of x will we run into trouble? Remember, we never want to divide by 0. So if I try to plug a 1 in there, f of 1, I get 1 to the third minus 1 divided by 1 minus 1. And if I do the numbers there, 1 to the third is 1, minus 1 is 0, divided by 1 minus 1 is 0. We cannot ever divide by 0, so how in the heck would I ever graph that? Well, the idea here is going to be to not plug in 1 directly. We're going to plug in numbers very, very, very close to 1 and see what we get that comes out as our y value. So we are going to be able to graph this. The thing is, we're going to have a hole in the graph at that naughty x value. When x equals 1, there will be a hole in the graph or something else going on. Go ahead, divide by 0 and see if I care. You know, this is what's going to happen if you try to divide by 0. That or worse. So let's get close to 1 and see what's really happening here. Here's our function again, x to the third minus 1 over x minus 1. We know we can't plug 1 in directly because it'll be undefined. So here on our table is our x value of 1, and we put a question mark down there because you can't divide by 0. We don't know what's happening. But first, let's approach that x value of 1 from the right-hand side, from numbers bigger than 1. So if I plug 1.25 into this function, and I do 1.25 to the third minus 1 over 1.25 minus 1, and I divide that out, I get a y value of about 3.813. And that's something I can graph. You know, on the graph I can plug in this x value, I can get this y value that goes with it, and I can graph it. But, you know, 1.25, it's close to 1, but we can get closer. Let's get a little closer at 1.1. And we plug 1.1 in for x, and we put it to the third power, subtract 1, divided by 1.1 minus 1. We get a y output of 3.310. And you know 1.1 is close, but let's get closer. Let's plug a 0 in there between the decimal point and the 1, and now have an x value of 1.01. And the y output that comes with that is 3.03. And we can even get closer to 1, 1.001. And we plug that into the function and get 3.003 as an output. So we were approaching our x value from numbers above or from the right, and we were approaching here, it looks like a 3. 3.8, 3.3, 3.03, 3.003. So it looks like we might be getting close to 3. Let's check from the other side, from the left side, or the numbers less than 1. Well, less than 1 is 0.75. We plug it into the function, and we get our y value of 2.313. But let's get closer to 1, 0.9, and we get a y value of 2.7. We get even closer, 0.99, and we get our y value of 2.97. Even closer is 0.999, and we get our y value of 2.997. If we look at these numbers on either side here, 2.997, 3.003, what's right in between those numbers? It looks like we're approaching 3. So if we actually did graph those points, what would it look like? Here's our function again, x to the third minus 1 over x minus 1. It looks like a parabolic curve. But this parabolic curve does have a hole in it at this naughty x value. If we try to plug in 1, we get a divide by 0 scenario, and we can't have that, so we get a hole in the graph. And that hole in the graph is actually our limit. And again, what we were doing, we were approaching x values, the x value of 1 from numbers above 1 and from numbers below 1. And what we were sort of doing was, when we plugged in numbers above 1, we were kind of sliding down this curve toward the hole in the graph. As we plugged in x values less than 1, we were sliding up the curve toward that hole in the graph. That hole in the graph is our limit. You know, that y value at the height of the hole in our graph is 3. So the limit of our function f of x as x approaches 1 is equal to 3. And we can write that, you know, in our new calculus notation. I think we'll see this on the next slide. The limit, the LIM, the limit as x approaches 1, so under it we'll have our little subscript x approaches 1, the limit as our x values approach 1 of our function f of x, or I could just have rewritten the whole function, that limit is equal to 3. Usually if there's a hole in the graph, the limit is the height of that hole on the y-axis. So the graph of f is a parabola that has a gap at that point 1, 3, as shown in the figure on the previous slide. Although x cannot equal 1, we can move arbitrarily close to 1. We can get infinitely close to x equals 1. And as a result, f of x, our output, moves arbitrarily close to 3. Using our limit notation, we can write it like this. I just showed you that on the last slide. And how we read that in English is written here in red. This is read as the limit of f of x as x approaches 1 is equal to 3. And this discussion leads to an informal definition of a limit. If f of x becomes arbitrarily close to some number L as x approaches some number c from either side, the limit of that function f of x as x approaches c is the number L. This limit is written as the limit as x approaches c. You know, our x value is approaching some number c, of our function f of x. Well, that limit is equal to L. L is a number on the y-axis, the height of the function at that given x value. So what we did with our table in that introductory slide was we estimated a limit numerically. And we're going to do that here in example 1. Evaluate the function f of x equals x divided by this denominator, root of x plus 1, that quantity, minus 1. And we're going to do it at several points near x equals 0. And then we'll use those results to estimate the limit. So here's our function. The limit as x approaches 0 of x divided by this denominator, root of x plus 1 quantity, minus 1. What happens if we plug a 0 in for x? Well, our numerator would be 0, and our denominator would be 0 plus 1 under the square root, and the square root of 1 is 1, minus this other 1. So again, we're going to get 0 divided by 0. So that means we're going to have to check this numerically, make an estimate of it. We're going to take numbers on either side of 0, close to 0, and see what our limit approaches. When we do these in class, we'll do these on the TI-89 calculators. It's real nice to put this function into the y editor. You know, you go to y equals, we plug in the function. Make sure you group off that denominator, parenthesize off that denominator, so when you hit enter, the function should look just like this in your calculator display. And then we will go to the TI-89's table feature, and we'll plug in these x values. We'll plug in this x value, get the y value that goes with it, this x value and the y value that goes with it, and so on and so forth. And we'll see what number we're approaching from either side as x gets closer and closer to 0. So I usually like to start from the numbers above, from the right. The calculator, I have this function put in there. I plug in my x value of 0.01, and I get an output of 2.00499. And then I get closer to 0, and I plug in this x value, and I get 2.0005. And let's get closer to 0. Plug this into that table again, and I get 2.00499. 4 zeros and a 5. 1, 2, 3, 4 zeros and a 5. Here we had 3 zeros. Here we had 4 zeros. We could plug in, I imagine, 0.00001 and get an output of 2 point and have 5 zeros and a 5. If we approach from the other side, from numbers just under 0, these smaller negative numbers, if I plug in negative 0.01, my output value is 1.99499. And if I plug in this next negative x value, 0.001 negative, I get 1.99950. The last one here, this negative 1, I get 1.499995. And again, the ones really close to 0 are the ones we're interested in. What number is right in between these two values? 1.99995 and 2.00005. Right in between there, it looks like we're approaching 2. So there we estimated it numerically. We just plugged in numbers really, really close to our given number that we're interested in. I like in the Calc for Dummies book, they call this your arrow number. What number comes right after x? We have x, arrow, and then we have a number. Again, I might refer to that time every now and then as our arrow number. As x approaches this number that we're interested in, what values are we approaching on the y-axis? It looks like here we're surely approaching a value of 2. If we were to graph this on the TI-89, if you hit the graph feature, you already have that in your y-editor, we would get the graph that looks like this, and on our calculator you're probably not going to be able to see that hole in the graph, but we do know that that hole exists. If we try to plug 0 in to our function, we get a divide by 0 scenario. The world's going to blow up, so we know we have a hole in the graph at that point. And the hole in that graph is right on our y-axis at a height of 2. So from the results shown in the table, we can estimate the limit to be 2. This limit is reinforced by the graph. In example 1, note that the function is undefined at x equals 0, and yet the function f of x appears to be approaching a limit as x approaches 0. This often happens, and it's important to realize the existence or the non-existence of our function at that given x value has no bearing on the existence of the limit of the function as we approach x approaches that value c. Alrighty, in example 2 here we're going to find a limit. Find the limit of the function f of x as x approaches 2, where f is defined as, here we have a piecewise function. Our f of x, our output value, is equal to 1 for all values of x that are not equal to 2. If we do plug in an x value of 2, our function value, our f of x, is 0. And this is kind of a confusing piecewise function. We don't see many variables in there. But if we come down here and think about it graphically, here's all our given x values. No matter what x value we plug into the function, no matter what it is, as long as it's not 2, our output value is 1. So here at y equals 1, we almost got a solid line running horizontally, except for one critical point. When x is 2, our function value is 0. So here at 2, our function value is equal to 0. We got a dot here on the x-axis at 2, and right above it is a hole. It's almost like, let me switch over this. It's almost like we had this horizontal line, and we just picked this one x value of 2, and we dropped that value right down here to the x-axis. So we got a horizontal line with a hole in it, but we do have, that function is defined here at 2. If I back up to this one, this example we just did, we had a hole in the graph, and there was no defined point above or below. If I plug in x is 0 and I look up, the graph is not there, I go right through the hole. If I look down below, there is no defined place of that function. On this one, there's a hole in the graph, but if I plug in an x value at 2, I do get this output value right here at a y value of 0. So our solution is, because f of x equals 1 for all x's except x equals 2, you can conclude that the limit is 1. Again, usually the limit is where the hole in the graph is. If I plug in numbers above 2, I'm moving along the horizontal line toward the hole this way. If I plug in numbers less than 2, I'm sliding along the horizontal line toward the hole in the graph. So the limit as x approaches 2 of our function is equal to 1, even though f of 2 is equal to 0. Just because our function is defined at the point does not mean that the limit and that value are the same. Here, f of 2 is equal to 0, but the limit as we approach 2 is equal to 1. I hope that makes sense. Alrighty, so far in this section, we've been estimating limits numerically and graphically. Each of these approaches produces an estimate of the limit. In section 2.3, in our next section, that should be a 2 because I'm in a different edition of the book, you will study analytic techniques for evaluating limits. Throughout the course, try to develop a habit of using a 3-prong approach to problem solving. The numerical approach, construct a table of values. Graphical approach, draw a graph by hand or using a calculator. Or the analytic approach, using algebra or calculus. And I mentioned at the beginning of the video, there are times when limits do not exist. In the next 3 examples, we're going to examine those 3 times when some limits fail to exist at all. So our first one here is example 3, behavior that differs from the left and the right. Earlier when we were doing our tables, here they were both, when we approached from the right hand side, when we approached from the left hand side, we were approaching the same number. That's not always going to happen. And usually a dead giveaway for that not happening is you're going to see some absolute value bars somewhere in your function's name. So here we have the limit as x approaches 0 of absolute value of x divided by x. So let's start here on the positive side. Let's say what happens if we plug in a 5. If we plug a 5 in there, we'd have the absolute value of 5 divided by 5. The absolute value bars make sure that 5 is positive, which it already is, so we get 5 divided by 5 is 1. So here's our y value, our height of 1. Our function is defined there at 1. What if we plug in 4? The absolute value of 4 divided by 4 is also a value of 1. And what about 3? The absolute value of 3 divided by 3 is 1. And also for 2 and 1, no matter what we plug in here on the positive x values, we're going to get some number divided by itself, and anything divided by itself is 1. So as we're sliding along here, we're approaching 1. We're sliding in here toward a height of 1. But remember, our arrow number here is x approaches 0. We cannot do 0 divided by 0. So as we get closer and closer to 0, we know there's going to be a hole in the graph. So here in positive x country, our graph is going to look like this. But what happens if we plug in negative numbers? Let's start here at negative 3. The absolute value of negative 3 divided by 3. Here the absolute value bars do their work, and they make that negative 3 positive. We get 3 divided by 3. Or negative 3, excuse me. We're plugging in negative 3 for x, so that's the absolute value of negative 3 divided by negative 3. So now we got 3 over negative 3, or negative 1. So here, we're going to be defined at negative 1. And if I plug in negative 2, same thing. The absolute value bars take care of the numerator, and I have 2 divided by negative 2, which is negative 1. So again, we're down here. Same thing for negative 1. And again, as we approach the arrow number of x equals 0, we know we have a hole in the function. So if we look at it this way, we're approaching 1 when we come from the positive side. But if we approach from the negative side, we're approaching negative 1. So the behavior differs from the left and the right. Later on, we're going to look at those. We'll have single-sided limits. They're called one-sided limits. But for now, we're just going to look at it as a whole. We're approaching different numbers from the left and the right. So this limit does not exist. The limit as x approaches 0 of the absolute of x over x, d and e. It does not exist. The limit from the left and the right have to be the same. Again, as we're approaching here from left, we're approaching negative 1. As we approach from the right, we're approaching positive 1. Those numbers are different, so the limit itself does not exist. That's our first instance where the limit fails to exist. In example 4, we're going to do the unbounded behavior. Remember, a limit is a number. It's a number somewhere on the y-axis. Each of these numbers could be the limit. Our limit is 1, our limit is 2, our limit is 3 or 4. A limit has to be a number. Oops. So sometimes we might have what they call unbounded behavior. So let's approach from numbers above 0. Again, we can't plug in 0. We're interested in 0. What happens as we plug in a value of 0? Well, what happens if I plug x as 1 in there? I'd get 1 over 1 squared, or 1. So our height here, let's call this 1, our 0.11. What happens if I plug in a half? Well, 1 divided by a half squared. A half squared is a fourth, or 0.25. 1 divided by a quarter is 4. So it would be somewhere up here. 1/2, comma, 4. Now let's get real close to the value of 0 and put in 1/10. Well, 1/10 squared would be 1/100th, or 1 divided by 0.01. 1 divided by 0.01 would be 100. So we'd have to go way up here off the slide I'm using. So it looks like the graph is going up, 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 up. And think what happens if we get even closer. 1/1,000,000th. Well, 1/1,000,000th squared would be an incredibly huge, or an incredibly tiny, tiny fraction. And when we divide that into the numerator of 1, it would be a huge number. We're going way up. We're approaching infinity. What happens if we approach from the negative side? Well, 1 divided by -1 squared. -1 squared is 1, so we'd get 1 divided by 1, or 1. If we plug in -1/2, the square part of our function, remember we're squaring our denominator, that's always going to make it positive. So if we plug in -1/2, we're going to get the same y output of 4. -1/2, comma 4. If we plug in -1/10, we'll get the same thing, positive 100. So our graph again is going up, up, up. The closer we get to 0, the bigger and bigger our number gets. And so it looks like we're heading off toward, again, infinity. And remember, infinity is a concept. It's not a number. A limit is an actual number on the y-axis. Infinity is not a number. You can pick any number, and there's always a number bigger than it. So here, our limit fails to exist. The limit, as x approaches 0 of our function, 1 over x squared, dne. It does not exist, and the reason is unbounded behavior. Unbounded behavior is the reason. And let's open what we got down here. Because f of x is not approaching a real number, again, L is a number on the y-axis somewhere, as x approaches 0, you can conclude that the limit does not exist. Okay, and our last instance of limits failing to exist occurs because of what is called oscillating behavior. And now our function is the limit as x approaches 0 of the sine of 1 over x. So let's see what happens here. We have our sine 1 over x. What happens when we plug in 2 over pi? So we're going to have the sine of 1 over 2 divided by pi. And we can, we have a fraction divided by a fraction, so we invert and multiply. This turns into the sine of pi over 2. And what is the sine of a half pi? I hope you remember your unit circle. Sine of a half pi is -1. Oh, that's not -1, it's +1. Remember our unit circle. Here we have, that would be 0, 1. This would be 0, comma, -1. Our sine value, this in radians, is pi over 2, so our sine value is the y-coordinate. The sine of pi over 2 is +1. And when we plug in 2 divided by 3 pi, just like here, down here would be 2 divided by 3 pi, we invert and multiply, so that's the same as the sine of 3/2 pi. And the sine of 3/2 pi would be down here, -1. If we plug in the next given x value, 2 divided by 5 pi, again we would invert and multiply, and that would be the sine of 5 pi over 2, which takes us back up here to positive 1. And 2 divided by 7 pi, we would have the sign of 7 pi over 2, which takes us back down here, which is negative 1. And you're going to notice a pattern. Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. And notice our x values are getting smaller and smaller. Our numerator is always 2. Our denominator is growing bigger and bigger. 1 pi, 3 pi, 5 pi, 7 pi, 9 pi, 11 pi. So that means our denominator is growing, our numerator is constant, so the fraction itself is getting smaller and smaller. It is approaching 0. If we continue that pattern, the smaller and smaller we get, we're just going to keep alternating back and forth between 1 and negative 1. And if we look at the figure here, as we get closer and closer to 0 on the x-axis, we're heading this way. Closer and closer to 0 on the x-axis from the negative side, heading this way. We're bouncing back and forth between 1 and negative 1 at an increasing speed. So that means, we're constantly bouncing back and forth. The closer we get to 0, the faster that's going to happen. And remember, the limit is a number on the y-axis. We're not approaching any one number. We're bouncing back and forth between two numbers, 1 and negative 1. Now, this would be a good time. Graph this function on the TI-89 and compare it to this graph on the left. We know this is what the graph is going to look like, but what does our TI-89 spit out? It's going to look something like this, really weird in the middle. When you use a graphing utility to investigate the behavior of a function near the x value at which you're trying to evaluate the limit, remember you can't always trust the picture that graphing utility draws. If you use a graphing utility to graph that example 5 over an interval containing 0, the origin, you're most likely going to obtain an incorrect graph, as shown here in the figure. The reason the graphing utility can't show the correct graph is that the graph has infinitely many oscillations over any interval that contains 0. So be careful with those calculators. So, common types of behavior associated with the non-existence of a limit. If the function approaches different numbers from the left and right side, the limit does not exist. If f increases or decreases without bound as we approach our number c, the limit does not exist. Or if our function oscillates between two fixed values, the limit does not exist. So let's do a quick little wrap up here, just some quick examples. This will help out with some problems in the book. And hopefully it'll see the difference between the value of the function and the limit as we approach maybe that same value. So I look here at part A. What is f of negative 2? Well, if I go on my x value to negative 2 right here, and I look above or below the function, is the function defined above or below me? No, we got a blue dotted line. It looks like we have a vertical asymptote. So this is undefined. The function's not defined above or below. The function does not exist above or below the x value of negative 2. Part B, what is the limit as x approaches negative 2? Well, if I look here, if I approach negative 2 from the left-hand side, it looks like my function's headed down toward negative infinity. If I approach negative 2 from numbers above negative 2 from the right-hand side, it looks like the function is headed up here toward positive infinity. So this limit, dne, it does not exist due to unbounded behavior. All right, part C. What is f of 0? Well, if I go to x is 0, and I look down here, I don't see the function anywhere. If I look up, I go through this hole, and I hit the function right here. We are defined right there at a value of 4. So f of 0 equals 4. But what is the limit as x approaches 0? Well, if I approach 0 from the left-hand side, sort of sliding down the curve here, it looks like I'm approaching 1/2. But if I approach 0 from the right side, from numbers above 0, it looks like I'm sliding along this part of the graph, and it looks like I'm approaching a height of 4. If I approach from the left, it's 1/2. If I approach from the right, it's 4. I'm approaching two different numbers. So that limit does not exist, because I'm approaching two different values. Let's see here. What's the next one? Letter E. F of 2. If I go to my x value of 2 and I look down here, I don't see the function anywhere. If I look up, I almost hit the function, but I go right through that hole and I keep on going and I never hit anything again. So f of 2 is undefined, just like f of negative 2. But for letter f, what is the limit as we approach 2? Well, if I approach 2 here from numbers under it, I'm approaching this hole in the graph. If I approach from numbers to the right, from numbers greater than 2, I am approaching that exact same hole. I'm approaching the same number from each side, so that's my limit. And just by eyeballing it, it looks like that limit is 1/2. Okay. Letter G, what is f of 4? Well, I look on my x-axis at 4. If I look down, I don't see anything, but if I look up, boom, I hit this point. So f of 4 has a height of 2 on the y-axis. What is the limit as we approach 4, though? Well, if I approach 4 along the x-axis from the left side, I'm sort of sliding along this curve, and I'm heading up, 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 looks like toward infinity. If I approach from numbers above 4, I'm sort of sliding along this part of the curve, and I'm also going up, 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 up toward infinity. And remember, infinity is not a number, it's a concept. So this limit, dne, it does not exist. And why not? It's due to unbounded behavior. So graphically, look for holes in the graph or unbounded behavior. Remember, if they're asking for f of a number, that's just where the function is defined, if it is at all. So you should be able to do all the homework up through problem 25 on your assignment sheet. You see these problem numbers, 31, 35, and blah, 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 blah. Cross those off. Those are the problems that deal with the formal definition of a limit. Again, I was advised not to teach the formal definition of a limit. Save that. I used to spend a couple days on that formal definition. Much better spending those days on other parts of calculus that will get you more ready for the AP exam. So cross off all these numbers on your assignment sheet.